and Matthias Röger. Hans-Christoph Gruner is a colleague of mine from Magdeburg, and Matthias Röger is at University of Dortmund. So I start with a general description of the Willmore functional before I go to the more special case which I'm interested in. So the Willmore functional can be described as follows. Suppose you have an immersion F defined on a two-dimensional reference manifold. At the moment, it can be a manifold without or with boundary into R3, an immersion. And then you obtain as the image a two-dimensional surface in R3. And then you associate with this surface the following value, the Willmore functional at F defined as a quarter times the integral over m h squared d mu, where h is the mean curvature of the surface. In my notation, it is the sum of the principal curvatures rather than the average of the two principal curvatures, and the mu is the measure induced by the immersion F. So that's the Willmore functional. And so it's defined in terms of a geometric quantity, and the original interest is also in geometry, so in particular in conformal geometry. And the main reason for the interest in conformal geometry is the following property of the Willmore functional. It has an invariance property with respect to conformal mappings in R3. So if phi is a conformal mapping in R3, then the value of the Willmore functional is unchanged. And conformal mappings, so for all conformal mappings. So for example, translations, scalings, orthogonal transformations, but also the sphere inversion. These are conformal mappings, and then also compositions of those. So that was the reason why it was originally, people were interested in geometry in it, but there are also applications in, for example, in membrane physics, or also in image processing. So for example, in membrane physics, there is a modeling of biomembranes which uses a generalization of this functional. This goes back to Kenham and Helfrich. This was in 1973. And the generalized functional, also known as the Kenham-Helfrich functional, looks like this, and denoted by W tilde. It's got additional terms in it. There is a term penalizing area. Then there is a term which also involves the mean curvature minus some called spontaneous curvature, H naught. And then also another term which involves the Gauss curvature, K. So K is the product of the principal curvatures. So in these applications, quite often one is interested in minima for these functionals. And so the first step would be to look at the first variation and equate it to 0 in order to get the Lagrange or the Lagrange equations. So, and this leads to, if I go back to W, to the notion of a Willmore surface, which is just a stationary point for the Willmore functional. So the first variation equal to 0, and then one can do a calculation and calculate what does it mean for the surface, what does the equation look like, and it turns out that it's the following equation. This is the Laplace-Beltrami operator corresponding to the surface gamma, plus 2h times h squared minus k equal to 0 on the surface. And the important thing here to notice is that what you end up with is a fourth order equation for in the position of the surface. So h, when you write it down in terms of a parametrization, for example, this is described using second derivatives of the surface. Then there is a Laplace-Beltrami operator, again second derivative, so this is a fourth order term. It's already nonlinear here in the Laplace-Beltrami in the first order derivative, so this is not the usual Laplace, but it's a nonlinear expression in the first order derivatives. There are other nonlinearities here, h cubed, for example, that's a highly nonlinear expression in the second derivative. So this is quite a complicated equation. I'm not trying to solve it here. What is important for my talk is, since I'm interested in boundary value problems, about specifying boundary values, since this is a fourth order problem, I expect to have to prescribe two sets of boundary conditions. And that's why I mentioned this here, because that's what I'm doing later. So maybe a little bit more concerning the minimization. And one can distinguish closed surfaces. By this I mean compact surfaces without boundary. So closed surfaces. And there it is known that the infimum of the Willmore functional is attained for a sphere. And then the value is 4 pi. And you can take any sphere because of this conformal invariance. You can translate it, you can blow it up. It doesn't change the value of the functional. This is known. Then, of course, you can look at the situation when you minimize subject to prescribing the genius of the surface. So then this is more difficult, and there are existence of minimizers. This goes back to work by Simon, 93, and Bauer and Kubert. I think this was in 2003. They use methods from geometric measure theory in order to prove that there is a minimum of the Willmore function subject to a prescribed fixed genus, the surface. And there's one famous problem which has recently been solved, where one can say what the minimum is. That is related to the so-called Willmore conjecture, when you ask the question, what is the infimum when you prescribe the genus to be equal to 1? So you're looking at surfaces of the type of the torus, and it has been proved recently, and that was an open question for some time, that this is attained by the so-called Clifford torus. And the value is 2 pi squared. The Clifford torus is when you take an axisymmetric torus and you have two radii, a bigger and a smaller one, and the ratio is square root of 2 and 1 between these two radii. And this was proved by Marquez and Neves very recently. So they solved this Willmore conjecture. For surfaces with boundary, this is my second point here. So surfaces with boundary, less is known. So you have now to prescribe boundary conditions, and there are several possibilities. There is a nice paper by Nietzsche from 93 who lists possible choices depending on how you vary a given surface. So you have choices of varying surfaces. You can keep the position fixed and leave everything free. Then you get different boundary conditions compared to when you fix both this position and the normal at the boundary. So there are various choices you can make, and these are, can be found in the paper by Nietzsche. What we did together with several other people was to look at axisymmetric surfaces. So that's the following situation. You look at surfaces of this form. You take a curve and you rotate it around the x-axis. So that might look like this, and you get these axisymmetric surfaces where you prescribe conditions here on the boundary. For example, you fix the value here, and you also fix the derivative, for example. And then you come up with a boundary value problem essentially for a curve, and it's possible to prove existence of minimizers in this case. So this following people that are involved: Bergner, Delacroix, myself, Fröhlich and Grunow, for example, and others. So there are several papers where we have looked at problems like this for Dirichlet problems, which are just described, but it's also possible, for example, to prescribe then the mean curvature on the boundary and solve that problem. So that's a special case. There is a very general result by Rainer Schätzle, who has looked at the parametric description for surfaces in 2010.
Sorry, just a small question. If you only prescribe the position, what kind of natural boundary condition?
That's the mean curvature being equal to 0. That's sometimes called Navier boundary condition. So we decided, so this result here by Rainer Schätzle, just as these results by Simon and Bauer and Kubert heavily rely on geometric measure theory, is quite a, at least for me, difficult machinery. So what we tried to do was to look at graphs and hope that maybe one can do something using simpler methods. So now we are looking at graphs and the corresponding Willmore functional. So the situation is the following. I take a smooth bounded subset of R2, call it omega, and on omega we look at the graph of a function u. And as the set of definition, we take the following, call this M, the set of all u in H2. And now I include into this set boundary conditions. And what I do here is I prescribe u as phi on the boundary and also the normal derivative I prescribe. And then I look at the Willmore functional on for this graph, and this can be written down as follows. So I now write w of u rather than w of f. So that's a quarter integral over omega h squared, and then there is the area element. So q is for the graph, the area element is given by 1 plus gradient u squared. That's well known, and the mean curvature for a graph can be written down as follows with my convention that it's the sum of the principal curvatures. It's the divergence of gradient u divided by the square root of 1 plus gradient u squared, so divided by q. So this is the Willmore functional for a graph. And before I start talking about a minimization or properties, there is a first set of inequalities which is quite helpful to understand the difficulties when one tries to minimize. So you've got the following inequalities. I write note. If you start with the following expression, the full second derivatives divided by q to the 5. This is bounded from above by the integral over omega, the second fundamental form integrated over omega. So the second fundamental form the norm of the second fundamental form squared can be expressed in terms of these principal curvatures just by kappa 1 squared plus kappa 2 squared. And then you can relate this to mean curvature and Gauss curvature just by the following formula. H squared q minus twice the Gauss curvature. And now here what we have is up to a factor the Willmore functional, so that's nice for us. And the Gauss curvature, there is the famous Gauss-Bonnet theorem which you can use in order to rewrite this. So the first term is 4 times the Willmore functional. And now I don't write down exactly the Gauss-Bonnet theorem, but I just say that the Gauss-Bonnet theorem contains one term which is the Euler characteristic of the surface, which is for us fixed, a constant. And the second term occurring in the Gauss-Bonnet theorem is an integral over the boundary of the surface involving the geodesic curvature. And because we prescribe our boundary values here, it is possible to express this term in terms of our given boundary data. So what I simply do is I say that I can estimate this by something which depends on omega and the boundary data, so that I've got rid of this term at this point. So this is Gauss-Bonnet, which is behind this.
So, but this term doesn't have a sign.
No. And finally, in order just to show you that that it's finite, this term here can be estimated on the Willmore functional by, I write a constant times d2u squared divided by q plus 1. So this shows, since q is greater or equal to 1, that if you take as your set of definition h2, then the Willmore functional will be finite for these functions. But as you can see, the trouble now is, there is a point where it's difficult to continue. Once you have, suppose you have a minimizing sequence for W, what can you say about the U's? What you control is a certain quotient of second order derivatives divided by a high power of first order derivatives. So what does it tell you? And initially it's not really clear how it helps. And so what we first did was trying to derive some estimates. Suppose you have a bounded Willmore energy, what kind of classical norms can you bound? And this is the first result. I call this theorem 1. For all u in the domain of definition M, it's up there, we can prove that the supremum x in omega plus the integral over omega q dx is bounded by a constant times w squared plus 1. And the constant depends again on omega and the boundary data. So this means in particular here that you have control on the L1 norm of the gradient. So I just want to show you what is the idea behind this. And the starting point is the following calculation. You look at the following integral u times h dx. And the h is up here, the divergence of gradient u divided by q. So if you do integration by parts on here, what you obtain is minus. So you throw the gradient onto the u. So you get gradient u squared divided by q plus a boundary integral u times du by du divided by q. And the boundary term is fine for us because u and du by du are given in terms of phi. Q is greater or equal to 1, so this is bounded. And here you can add and subtract a 1. When you have the 1, then you get in the numerator q squared divided by q that goes out. And then there's a 1 over q in addition, but that's bounded by the measure of omega. So this is less or equal to minus plus a constant. And so you take this to the left-hand side. And so you can bound it by a constant plus. And now this here we are quite generous, and we didn't know how to improve it. So what we just do is first of all use some Cauchy-Schwarz inequality, L2 norm of u, L2 norm of h. And in the L2 norm of h, you even go further and add the q, because q is greater or equal to 1. So this will give you the square root of the Willmore energy. And here we have the L2 norm. And okay, we can't really do a lot with it when we just go to the supremum, because we will be able to estimate the supremum anyway. So supremum times the square root of the Willmore energy. So the question is, how can you deal with the supremum? And there is a following idea where we use a a general result by Leon-Simon. So the idea is the following calculation. You look at the supremum u of x minus the supremum of y on the boundary of phi of y. That's something which is known and fixed. And you can estimate this by the supremum x in y, on the boundary u of x minus phi of y. And this can be further estimated by the diameter of the graph of u. So this is a surface in R3, and there is a general result by Simon. So this is Simon, which gives a bound on the diameter of a surface, and this doesn't have to be a graph. This can be a general surface, a smooth surface. You can estimate it by a constant which only depends on the space dimension, and then the integral over the second fundamental form, the L1 norm of the second fundamental form, plus the diameter of the boundary curve, like this. So this is, of course, we rely very heavily on this result. This is quite a deep result by Simon. And now if we continue here, just using Hölder's inequality, to see this, I write this as square root of q times square root of q. And then you see this can be estimated by a squared q to the half times q to the half. The diameter of the boundary can be estimated because we know the boundary values. So another constant. And now we use this chain of inequalities which are written down here again, starting from a squared q. And then we end up with being able to estimate it by w of u plus a constant. Here you need the square root. So what you get is something like this. Plus 1. So this is roughly what it looks like. And the point now is, if you now go back, so this term you take just to the right-hand side. This is something which we know. So the supremum can be estimated by this expression over here, and it involves the integral over q, but to the power half. So if you insert it in here, then you have here essentially the worst term is the integral q to the half, and you can kick it back to the left-hand side. It has the power half, so it goes back to the left-hand side, and then you have an estimate for the integral over q in terms of just the Willmore energy and constants. And so that would be the first part, and then you use again the supremum estimate. Now you control q, and then you have the estimate for both. So that would be the first step. This is the kind of norms which you can control, and unfortunately we can't do much better. So we haven't been able to get better estimates. There are examples which suggest that not much more is possible. So if you now go back to the question of minimization, then and you think in terms of a minimizing sequence, what you now control is an L infinity norm, and if you look at it, an L1, the L1 norms of the gradient. So essentially you have a uniform control in BV. And it is known that then you have a convergent subsequence, strongly convergent subsequence in L1. And the limit would then be an L infinity function and intersected with BV. Unfortunately, we don't know how to, if you end up in this space, how do you define the Willmore functional in such a space? We don't know how to do it. And the way out here for us was to relax the functional and to consider the lower semi-continuous envelope. So that would be our next step, to introduce this envelope. And What it does help us is it gives us lower semi-continuity, and we have already coercivity in L1. And so we are able to do some minimization, but for a relaxed function. So how does this look like? So this lower semi-continuous envelope. I want here to mention, there are of course several papers, but something which is related to what we do is an older paper by Bellettini, by Maslow, and Pauline. But there are papers following this. They look at also at the curvature type function, but looking at the elastic energy, so for curves, and also use relaxation. They are actually able to precisely describe the lower semi-continuous envelope, something which we will not be able to do. So the formal definition looks as follows. So it's defined on L1 into 0 infinity, and the value is given as follows. Take the infimum over all the lim infs, they go into infinity, w of uk, where uk belongs to M and converges to U in L1. So you look at arbitrary sequences converging to U in L1. You take the lim inf, and then you take the infimum over all these possible sequences. And the first thing to observe is, first of all, there is an equivalent formulation for it, which says that this is also equal to the supremum, the pointwise supremum over all lower semi-continuous functions lying below W. And the first observation is that this W bar is lower semi-continuous, and also that W bar is less or equal to W for U in N. This is simply because here you can take the constant sequence, and then this is clear. But of course one would like to have more properties for W bar, and this is our second result. Ideally one could derive a characterization for this. Unfortunately, we are not able to do this up to now. I don't know whether it is possible for us. First observation is the following, that for all U and N, actually they coincide. So this means that W bar is an extension of W. So it turns out to be the largest lower semi-continuous extension of W. So that is some nice property. And then one would be interested in the domain of definition of W in the sense for which U is W bar finite. And we have some information about this. So if W bar of U is finite, then we can prove the following. U then belongs to L infinity intersected with BD. So this essentially comes out of what I've had in theorem 1, rather immediate consequence, more or less. If you have that, in particular if you have function in BV, then you have that the gradient is a Radon measure, a vector-valued Radon measure. You can write it down like this. So I denote the gradient or the derivative by du, and you can decompose it into an absolutely continuous part with respect to the Lebesgue measure, plus a singular part, which I denote by dsc. And now you can take this is a function, and one function with values in Rn. You can write down the following expression. The divergence gradient u divided plus 1 plus gradient u squared. So first of all, this might make sense as a function. Then you can look at the distributional derivative of that function, and it turns out that under this condition, this is an L2 function. So it belongs to L2. Further, you have the following estimate: h squared times 1 plus the gradient u squared is less or equal to w bar of u. So this is now something which works in the other direction from below, but unfortunately we don't know whether this is equal. This is a gap, and we suspect that this gap is related, of course, to this singular part, and we don't know how to deal with it. So this is something where would have to do some additional work. As concerning the boundary values, what we can prove is the following: that the singular part, so this is a measure on the boundary, is equal to 0, so it doesn't have a contribution on the boundary, and u is equal to phi, and the gradient of u is equal to the gradient of phi, almost h1 almost everywhere on the boundary. So in the sense that that these functions have representatives, and then you can talk about evaluation of these representatives on the boundary, and it turns out that almost everywhere with respect to the one-dimensional measure agrees with these given boundary. So in that sense, we keep the boundary data. So what I want to do is, as a short corollary, this is more or less an immediate consequence, but I think it's still worth writing down, is now you can minimize the relaxed function. There exists a function u in L1 such that w bar of u is equal to the minimum of w of v in L1, and this is equal to the infimum v in n w of v. So what you find is that the minimizers of w bar are exactly those functions which occur as L1 limits of minimizing sequences of w. So you capture in some sense with the w bar the limits of minimizing sequences of w, but in L1 conversions. And the proof is quite straightforward. So you take a minimizing sequence for w bar, and by the definition of w bar, you can take these elements in the sequence even in n. So there exists a sequence uk in n, so that w bar of uk, which is the same as w of uk by the first part, converges to the infimum of w bar, and I call it alpha. And then it turns out, then we know, since this converges, that the sequence w of uk is bounded. Then you have the bounds in L infinity and in BV. Then there is a convergent subsequence. So this means that this is from theorem 1. uk is bounded in BV. So it has a convergent subsequence, say, to u in L1. And then, since alpha is the infimum of w bar, alpha is less than w bar of u, and this is less or equal to the lim inf of w of uk by the definition of w bar, and this is equal to alpha. So w bar of u is equal to alpha. Minimize the w bar. That's quite immediate. What I want to do is to finish this off is to say something about the point A. How do you get the equality here between w bar and w? So this is justification for the use of w bar. suppose that, so this is idea for A. We already know that W bar is less or equal to W, so what you need to prove is that W is less or equal to W bar. Prove for U and N. And what you start with a sequence. There is a sequence K in N. All the elements of the sequence belong to M, such that the values W of UK converge to W bar of U, again by the definition of W bar as an infinum. And now one can use some geometric arguments. We introduce the normals to the graph of UK and to the graph of U. So that's 1 over QK. QK is the square root of 1 plus gradient UK squared. Gradient UK and 1. And same for the limit. So here I should say this, in addition that UK against U in L1. So these two have the property that they both have norm 1 as vectors in R3. And now you can look at the following expression. Half times UK minus mu squared times QK plus Q. So this comes a bit out of nowhere, but we will see that this is quite a useful expression. First of all, we note that this is greater or equal to 2, because it's the sum of two expressions which are both greater or equal to 1. And now you can rewrite this as follows. Using the fact that both are normalized to 1, you just calculate this, and then it gives you UK squared and mu squared. This gives you a 2. So with the factor in front, 1, and then there's the mixed term 2 UK mu, the dot product. There's a 2 in front with the half, looks like this. Next step is to rewrite this as follows. UK minus mu times QK mu K minus Q mu. Again, to check this, you multiply, then you have QK mu K squared. This is QK. The same here with the minuses, mu Q mu. This gives you a Q. So that's this sum here with the 1. And then you've got these mixed terms, mu K and mu K mu with the Q and the QK. So you've got this expression. And now what you observe is that this term here, the last component is equal to 0. If you multiply by QK, then the last component in both cases is 1. So it cancels out. So I write it like this. This means in the dot product here, between these vectors, only the first two components are counted. So, and they look like follows equal to gradient UK divided by QK minus gradient U divided by Q. And here, if you take the others, multiply by QK, then you've got here the gradient of UK minus the gradient of U. So what you can do now is you can integrate by parts. Note that everything belongs to H2. So both U and UK belong to H2. So I can do this. So what you get is then here the divergence on this one and the divergence on this one, but these are HK and H. Times UK minus U. And now this similar expression already occurred, and here again we can be rather crude. We estimate it by Cauchy-Schwarz inequality, and for the H, I just use the triangle inequality because I want here to use this difference in order to make this 0. So this is in the case the L2 norm. So this is bounded by a constant because I'm looking at the sequence WK, which is converging. The value is finite because I'm in H2. So these values are bounded. And here I have my L1 convergence, but I also have an L infinity bound coming from the boundedness of my Willmore energy from theorem 1. So this implies that this converges in any finite LP, also in particular in L2. So this goes to 0. Infinity. And since this term is bounded from below by 2, this means that mu k minus mu converges in L2. Mu k converges in L2. And then also almost everywhere for subsequence. And if you translate this into the components, then you have the following, that the gradient uk divided by qk converges to the gradient of u divided by q, and the last component, and here again almost everywhere. And now you can go on and look at the H case, the divergence. And so what it gives you is that HK weakly converges to H in L2. So if you take a test function here, a smooth test function, phi AK, integrate, and you do integration by parts, and then you use the convergence over here. Maybe I can do it in more detail. Gradient UK divided by QK times phi. After integration by parts is this gradient phi. And now you use this pointwise convergence. This is also bounded here. This is bounded by 1. So you have that this converges to gradient u divided by q times gradient phi, and then you go back to the h times phi. So you have weak convergence of hk to h and L2. But we would like to do it a little bit better. We would also like to include the qk, because in the value of the Willmore functional, you have h squared multiplied by q, and so this is not yet enough here. And that's the last step. So the claim is that also this holds. Times the square root of qk converges weakly to h times the square root of q. And to see this, again you take test function, smooth function phi, and you write this as follows. hk, and here you take the q times phi plus correction ak square root of qk times 1 minus, and then you have q divided by the square root of qk times phi, so then everything is okay again. And this is now an L2 function. If phi is smooth, which we can take as the infinity function, 0 infinity. Since q is in L1, this is in L2, and then this converges to integral by what we already know, to h, because hq converges weakly. And so it just remains to discuss this term here. this part here is bounded in L2, because when you take the L2 norm, you've got hk squared times qk, but that's just the Willmore energy up to effective. It's bounded. So one needs to look at this term here, and because of what we know, we know that this converges, you just multiply by q, then it converges pointwise to 0. So to 0 pointwise. But you also have a bound. You can use Lebesgue's dominated convergence theorem within L2. So if you take the L2 norm of this expression here, it's bounded uniformly in K. And then this means that this term goes to 0. As K goes to infinity. So this means we have this V convergence, and this implies that the integral h squared times q, this is just 4 times w of u, is less or equal to the lim in, because of the V convergence, hk squared qk, but that's the 4 times w of uk, and this goes to, this was written here, to w bar of u. And so we also have the second inequality, which we wanted to prove, namely that w is less than w bar. So they are both equal. And I think I stopped you. You can make it later.
So just a small question. This last result implies that if you could now prove enough regularity of your minimizer, then you would have solved the problem.
Yeah. Yeah. That would be regularity theorem. I think is quite difficult.
Yeah, but the last result reduces the problem to this.
Question, because this there in the inequality on around the middle of the board.
This one?
No.
Yeah.
Of course, you miss a possible jump part,
Yeah.
and it's not. I would say it should be possible to reach a function which has a jump part actually, and which has curvature on the jump part. No?
Yeah.
Did you try to make examples where you could?
That's something which we want to do. Yeah, we haven't yet done.
Of course, then maybe with the boundary condition, maybe it's impossible to reach when you minimize. I don't know.
Yeah, and also there might be another Cantor part in it. So there's something we.
There might be, because I would say there is not, but I don't think it's.
I also would
easy.
expect
I
there
don't think
not to
it's
be a
easy.
Cantor part, but I.
Because it should have very big curvature.
Okay, yeah.
Oscillating,
But we haven't been able to exclude it. But yeah, I would also
it should
suspect
be
that
very,
it's
very difficult to. And also here, you assume that if you don't assume that U is in H2, but you still can consider your sequence, your minimizing sequence, and you still have that nu is a Cauchy sequence in L2, and you cannot derive anything interesting out of this.
We haven't followed this path. So when in the paper we have used a different argument. So this was just here to simplify the presentation. So I'm not sure what one could do with it. In the paper, also in order to get the boundary conditions, we've done a different thing. What we did is, in order to exploit these inequalities, which at first sight seem rather useless because it involves these quotients. So what you can look at is suitable powers of 1 over q to the, and then some derivatives of this. When you calculate, it turns out that a corresponding sequence is bounded in H1. Because when you calculate derivatives, there are second derivatives appearing. If the power is high enough, this will lead to an H1 estimate on here. And we used these sort of arguments in order to do these things and also to deal with the boundary conditions. So that's the idea. So that's why we didn't really follow this path, but it's probably worthwhile doing it.
consider the Willmore problem with this in this setting, in the sense that you have boundary data on a curve. What's known about the surfaces?
You mean the...
Take a curve which is in a plane, take smooth Dirichlet data, and minimize the Willmore function.
Well, there is this Reiner Schätzler who's minimized in more general situations, who's getting a minimizer which is smooth up to a finite number of points, and if the Willmore energy satisfies a certain smallness condition, is also smooth without any.
What does it mean, smooth up to a finite number of points?
There are branch points, so the immersions mapping F is not regular. And you can then do some asymptotics close to it.
And then if you translate that, if you look to it, you have such a minimizer, and you look at. Are you in Cambridge? This before you. I know you have.
I just have to leave now.
Yeah.
I am here.
Like yeah.
Except on Monday and Tuesday.
Okay.
G118.
Sorry. How would it translate to what the graph would look like?
We don't know.
Because in principle, I suppose, this is the singularities that you see in the graph case somehow or other got to be because this surface is no longer a graph.
Yeah. This is the problem, that there might be situations where we prescribe boundary conditions, and the best the Willmore energy can do is not being a graph, but somehow coming back on itself, and then what we then see probably will be these steep gradients or these jumps in the solution. But it's difficult to read it out of Reiner Schätzler's result. At least I wouldn't know how to do it.
Any more comments?
What about more complicated? Suppose you'd have a non-simply connected domain. This would be an interesting problem to look at.
I mean, we haven't made any assumptions here, omega being simply connected. So that wouldn't be a problem if you accept that this is a reasonable solution. That could be handled. Would just, for example, change the Euler-Poincaré characteristic in the Gauss-Bonnet theorem, but the properties of omega is just that it has to be smooth, and also the boundary data phi have to be smooth, so that we can calculate, for example, geodesic curvature and estimate it.
And there's a question of finite element approximation.
Yeah, so I mean, what we do at the moment, or what we have done, is looking at the gradient flow, for instance, the Willmore flow, in order to hopefully converge to a minimum, at least a local minimum. So that's possible to do with finite elements, either by using splitting techniques or by using C1 elements. So that's possible. But we haven't looked at say directly at the station of only via the flow.
So what do you think is the usefulness of this result?
Well, I think if we could say more about the W bar, then maybe it is possible to maybe identify situations where, hopefully, where you actually have a smooth solution.
Isn't it? Yeah, it's obvious that there will be data where it will not work with a graph, right?
Yeah.
I mean, if the boundaries get very close at some point, and you.
That's I'm sure that is the case. But what we see when we do numerical simulations is that if you work on a circle and the values you describe are moderate, then there is no problem. The solutions are smooth, which you see. We don't know whether these are the absolute minimizers, because the flow only converges to a local minimum, but we don't see any singularities. But so we haven't tried to somehow tune the boundary data in such a way that
sequence, it converges to a minimizer of something.
Yeah.
And it's not doesn't just converge to something, it can converge to a minimizer of something.
Yeah.
And if the other thing is if you can see that it's smooth in some sense, then it's in the sense of u belong to M at the limit, and that's good as well. And the next question would be is if you suppose you were to take boundary data, which is small in some sense. Certainly you would not expect it's very small, then you would expect there to be, you would expect the minimizing sequence to converge to something in M. If the boundary data is very small, because it would be close to being flat. But it would be nice. But it would be nice to be able just to say that there exists a constant such that if norm of phi in some set, or some norms of phi are less or equal to that constant, then there exists a minimizer of W.
Yeah. That's something which we are certainly interested in. We haven't been able to do it.
But then that gives you a target for a numerical computation, because then you can justify a numerical computation by finite element method, etc., etc. I guess. But I mean, is there any real value in, from the point of view of someone who wants to compute a Willmore surface, what could the real value of knowing more explicit expression for W by U be?
From the computational point of view, I don't know. From the computational point of view, you probably would just start your calculation and then see what you get without looking at things like this. So I think this is mainly a theoretical result, and I wouldn't think that it's of real value for someone interested in computations. Of course, that person should be aware of the possibility that if you start with a graph, that you might lose that property.
No, I guess, but I'm starting from that perspective.
But,
so, I mean, if you know W bar U, then you can be nice. It's nice from the purely analysis point of view, but from studying, from the point of view of studying the Willmore problem, what would its value be?
Suppose you were able to say more about W bar, maybe even able to locate the points or curve in omega where you have this jump. That could be of help.
Would you expect non-smooth solutions at all which are graphs? Or no, sorry, how would I say that? Would you, in case the Willmore, so the non-graph solution is not a graph, then you expect irregularities.
Yeah,
but
jumps.
Would you also, in other cases, when the expect irregularities?
No, I think, and somehow this says nothing happens on the boundary, well, in a certain sense here, because the singular part, it's somewhere I wiped it out. So then the singular part on the boundary is equal to 0. So we expect the problem to be in the interior of omega rather than on the boundary. This is a bit different from the when you do the minimize the area function. There's also possible to do in BV, where you expect if there's trouble, you lose the boundary condition. And this doesn't seem to be the case here. But of course, we are looking at the function with second derivatives rather than the first.
So, I mean, could I imagine there's a curve on which, just suppose there's a curve on which the derivative is, the gradient is infinite and bounded. Then you might ask the question away from, is there a setting where actually that the graph is a Willmore surface? Is that possible?
I mean, you could think of a situation where this comes from rotating a smooth Willmore surface.
Yes.
So I think that might be the problem, and we've examples constructed not with Willmore surfaces, but situations where you have a smooth surface and then you rotate rotate it in such a way that you get an infinite gradient, and it's just the wrong description of the surface. So you can have smoothness, but the graph description is just the wrong description. And then you have
Can you imagine a graph description which has been correct, but it's just wrong on a curve? And so maybe your minimizer is actually gives a Willmore surface. Is that possible?
I can't imagine it. I wouldn't exclude it, but I can't imagine it.
Question on the model with the name of Helfrich, sometimes people you connect constraints of given area and enclosed volume. I mean, here, of course, in your case, a given area would maybe be a possible site constraint. Is there anything possible there, or is there?
Yeah, the trouble would be, as far as I can see immediately, the trouble is passing to the limit in the constraint. Because what we have is, maybe it works, but we have L1 convergence only and V convergence in VV somehow. So I'm not sure whether this is enough.
You have some convergence of Q, right? That's all you basically.
Yeah, so here in this situation we do have convergence of Q. But that's in the situation where you want to prove W bar is equal to W. If you only say start from a minimizing sequence without assuming anything about the limit, then it might be difficult to pass to the limit in such a constraint.